So today my topic of this presentation is hybrid photovoltaic thermal solar energy systems. So I'll not go deeper into the technical aspects. Rather, I would like to give you some perspective about how to design the experimental setups, how to uh, how to approach numerical studies in this particular field. So this is the outline of today's presentation. I'll try to give a brief about the introduction, how this concept has been uh, taken up for research, and few designs about solar photovoltaic thermal collectors and the experimental approaches which I have followed. And I'll also try to give you a brief introduction about designing a solar simulator, then numerical investigation, and I'll try to briefly discuss some of the important results and results from my work. And finally, I'll conclude, I'll try to give you some of the important findings. So I think this is the most common slide from last 23 lectures. When we talk about energy, we straight away go to the different aspects of climate change. As we know, the global greenhouse gas emission has reached the peak level, and being an Indian, we are some way responsible because we are the third largest emitter of greenhouse gases in the world after China and United States. And if you look on the animated globe, this is published by NASA, we can see how the temperature of the world is changing from industrial industrial era to the present day. And this is a killing curve. It shows what is the carbon dioxide concentration in the atmosphere. This curve is updated every day by Mauna Loa Observatory in Hawaii, and the safe limit was around 350 ppm. Like 350 ppm of carbon dioxide was safe limit in the atmosphere. But presently we are at the level of 410 ppm. So I think we are far ahead of the safe limit. So we need to worry about the climate change. So the results of climate change, we can feel it, we can visualize it, we can observe it, and some way we are also like experiencing it in the form of like glaciers are melting, climate frequent cyclones, as well as the temperature and the seasonal changes. We can feel that because the way December used to be colder, it's not now. So why solar energy is so prominent? Why the researchers, when they talk about renewables, why they put solar energy as one of the prominent one? Because the solar energy is available all around the globe equally. Because either mostly due in the between the tropics, like Tropic of Cancer and Tropic of Capricorn, uh, uh, most of the population in the world lives, and this is the area where the solar energy is received at its highest. And the annual energy potential from solar energy is around 23,000 terawatt, which is very much as compared to the present day consumption. And if the PV technologies are able to convert the solar energy on a very small amount of land, that is 0.2% of the land, with an efficiency of 10%, that will generate around 24 terawatt of energy, and which is around 11 terawatt above the current societal needs. That means this is very important system if we think from the need perspective. And in 2018, around 177 gigawatt of renewable energy was installed all around the globe. And out of that, solar PV was maximum. You can see this graph where the green bars represent the solar energy share among the renewables. So this is the highest. And when we look at the solar spectrum, as we know, this is the colorful region in the spectrum is the visible light. And when we talk about PV, the PV uses PV operates in the range of 300 to 1150 nanometer. It utilizes maximum of the visible spectrum, and some of the near infrared, and some from the ultraviolet, but most of the IR region remains unutilized. So these are the shortcomings of PV, because as we mentioned about the spectrum, most of the IR region is unutilized. But when solar spectrum or solar radiation falls on an object, it absorbs entire range of the spectrum, not only UV, not only IR, nor visible. It absorbs the entire spectrum. So this happens. This happens also with the PV modules. PV modules utilizes the visible region, but it absorbs IR as well as the UV. So when it absorbs the IR, the temperature of the PV modules goes up, and we can see from these curves, these two figures, as the temperature of the PV module or the operating temperature of the PV goes up, the power output of the modules goes on decreasing. And this figure shows for different PV technologies or PV cell technologies how this drop happens. And this is maximum for crystalline silicon, and unluckily the crystalline silicon is the most installed PV technology in the world. So taking view of this problem, we try to come up with a solution, and we can see for crystalline silicon around 0.45% decrease in the efficiency with per degree rise in temperature has been reported. So while overcoming this problem of decreasing the efficiency with increase in temperature, we come up with a solution where we try to combine both thermal collector and PV into a single system. What happens, like the heat generated in the PV can be extracted by circulating some fluid through the rear surface of the PV module, and or by combining a thermal collector. So the physics behind the decrease in the power output is because the open circuit voltage decreases significantly with increase in operating temperature. However, the short circuit current increases slightly, but this slight increase is insignificant in comparison to the decrease in VOC. When we calculate the power output, we go for the formula fill factor into ISC into VOC divided by VMIM. So from there we can feel how significant this decrease will be, VOC. So these are the major components in a PVT collector. So as we know, when we look at a PV module, the topmost layer is a glass. After that glass, there is an encapsulant layer that is called EVA, ethyl vinyl acetate. Followed by that ethyl vinyl acetate layer, the third layer is solar PV cells. And after that PV cells, another layer of EVA is there. That means the solar cells are encapsulated between these two layers of EVA in order to protect it from environmental factors like moisture or some other natural like pollutants. So followed by EVA, there is a Tedlar layer. This Tedlar layer acts as insulator. And after the Tedlar backsheet in PVT, now these are the components up to 1 to 5. These are the components that are generally present in a PV module. Now, when we talk about PVT, we add a absorber. The sixth layer is absorber, as we can see here. This absorber is nothing but this can be some tubes, metallic tubes or polymeric tubes, or maybe a metallic sheet where the tubes are welded or braced. After this absorber, we placed a thermal insulation. That means a PVT is combination of a PV module as well as a solar collector, solar thermal collector. So that white Tedlar used as backseat material, this Tedlar is exclusively manufactured by DuPont. DuPont has like in any of the PV module, you will find DuPont made Tedlers. So what are the benefits? Why we are so much like inclined towards PVT, or why the researchers are so much crazy about these PVT systems? There are various benefits. Let me read a fact. It has been estimated that by 2060, around 70% of the world populations are going to live in the cities. So in cities, as we know, there are space crunches. Like in a building, it is not possible that the roof area can be utilized both for generating PV, for installation of PV, as well as for installation of solar thermal collectors. So we need to come up with a system where like it will optimize the space. So this can provide us enhanced combined efficiency per area, this PVT. So that means from a same collector, we can generate both the thermal as well as electricity. Now we can see the combined efficiency. If we separately install a PV and a thermal collector, the combined efficiency comes out around 25%. Whereas for a PVT system of the same collector area, we can get a combined efficiency of almost 50%. The second rationale or second argument supporting PVT installation is that around 50% of the global thermal energy is consumed for space heating and domestic hot water generation. So this is a very big number. So when we install a PVT, it can give you low temperature heat. That means from PVT we can get, if we use it for domestic hot water generation, we can get hot water at around 40 to 45 degrees centigrade. Yes, that is very less as compared to the geyser which we install in our homes. But if we look from the energy perspective, suppose we have to heat water from 25 to 50 degree. But when we use PVT, we are feeding the water into the geyser at 40 degrees centigrade. That means now in the previous case, when no PVT was used, we need to heat up the water from 25 to 50. That means around 25 degree water temperature needs to be increased by 25 degree. That means MCP delta T, if we use the formula, we can calculate the energy, which will be a number, suppose X. Now, if we are using a PVT and we are putting the outlet of the PVT into the geyser, that means we are feeding the geyser with water at temperature around 40 degree. Now we need to, if we need to reach 50 degrees centigrade, which was the utility temperature, we just need to heat the water by 10 degrees centigrade. So again, if we apply the MCP delta T formula, then we'll get another number X1. And if we compare this X and X1, then X1 will definitely be lesser than X. In that way, we can save energy. Now, these are some of the designs or some of the already experimented designs of PVT. So few researchers used flow channels which is converging. They place this converging channel below the PV cells or PV module, and some fluids were circulated. Some use honeycomb type aluminum sheet, and they use air as the heat transfer fluid. And here in this case, here they use some graphite field. Graphite has been used as filling below the PVT module so that indirect heat transfer can be achieved. And in this layer, they placed a perforated sheet below the PVT and forced some air below the perforated sheet so that these perforations help in uniform distribution of air and that heats the solar cells uniformly. And maximum energy can be extracted through this type of arrangement, which is called impinging jet cooling. And these are some of the well-established commercial designs of PVTs. These are called BIPVT, Building Integrated Photovoltaic Thermal System. These are like prominent in countries like Canada or Denmark, Netherlands. They are utilizing it in their homes. And this is one of the such buildings. This technology is called solar wall. So here what they do, they place solar modules into the south facing walls of the house, and they use it for space heating. And there are some gaps behind these PV modules, and this air gets heated when sun shines, and they used to circulate through some HVAC unit into the indoor space. So these are again some of the experimental setups, how they carried out experiments. So now if we look at the efficiency trend of PVT, this line, the blue line tells us about the present day efficiency of PVT. This is the thermal, and what is the target that needs to be achieved in order to make PVTs compatible with the thermal collectors that are available in the market. So we need to reach this gap. That means this much amount of efficiency has to be improved. That where the scientists are targeting, like present day PVTs are having an efficiency that falls within the range below 60, but the collectors, thermal collectors at present, they are very efficient, which almost crosses around 60. So in order to achieve this mark, 60% efficiency mark, thermal efficiency mark, we need to improve the PVTs in terms of designs, absorber designs, as well as we have to look into various aspects of fluid mechanics, how we need to circulate the fluids, and also we have to target different designs of PVs. And if we look into the terms of electrical efficiency of PVT, it's like very comparable. Even PVTs has better efficiency than PVs. So what are the two issues? We have tried to come up with two major issues which needs to be targeted. One is the cooling uniformity. Cooling uniformity is connected with the PV part, photovoltaic part, because when we talk about PVT, there are two parts, PV module, as well as the thermal collectors. And the thermal efficiency is attributed to the thermal collectors. So we need to, if we address these two parameters, then we can get a better combined efficiency. So now I'll try to give you some introduction about my research, what I tried to come up with, and how I address those issues. So at the beginning, I'll give you some hints about my experimental setup, or what are the experimental approaches I have followed during my PhD work. These are the 4 modules we have developed in collaboration with Central Electronics Limited, Sahibabad. So this is a PSU. So we experimented with 100-watt modules. These are all polycrystalline modules. All these are polycrystalline modules. The setup, a collector, this is PVT, this is PVT. Suppose these all are PVTs. So A and B have the traditional collector setup. That means these have vertical oscillating tubes. These are vertical oscillating tubes. These tubes in A, the tubes are glued directly into the PV modules, backside of the PV modules. Whereas in B, we have come up with a setup where we placed these tubes above a absorber sheet, and these tubes are connected by welding. And finally, this absorber configuration, including the tubes as well as the sheet, we have glued onto the rear surface of the PV. And C and D, C is called rectangular horizontal. If we look into all the setups, in all setups, the inlet of the water or inlet of the fluid is at the edges of the PV modules or edge of the collector. But in this rectangular spiral, this input of the circulating fluid is at the middle point of the collector. So these 4 modules has been investigated thoroughly. Like we have carried out almost 2 years of experimental studies, both under indoor as well as outdoor conditions. So this is the outdoor setup. where we this is the collector from a fluid tank generally, or in our case we have used water as the circulating fluid or heat collecting fluid. So from tank we use a pump. From pump we fed this heat transfer fluid into the collector, and then from the collector heated fluid goes out and again collected in this tank. This is a very huge tank, almost 5,000 liter tank. So the temperature remains almost constant for inlet fluid. And here the collector, from the collector, the electrical parameters like what is the power output of the collector, what is VOC, ISC, these are measured using a IV analyzer. So the IV analyzer was developed by Solmetric. There are various types of IV analyzer you can use, but in our case we use Solmetric IV curve tracer. So, and again we like measured temperature of the inlet, temperature at the outlet, so that we can calculate the thermal efficiency. And we measured the solar irradiance with the very basic instrument, that is pyranometer. And you can go for high-end pyranometer also. There are Kipjon, and then for our case we have used Apogee MP100. And we also measured the thermal characteristic of the surfaces, like when we use the circulating fluids, what is the temperature profile of the surface of the modules. We measured that. We used thermal imaging that was carried out through testo thermal imager. So this is the most basic. I'll say this is the most basic experimental setup that can be constructed anywhere at the very minimal cost. You can also find some replacement for IV curve tracer. And this is the indoor test facility we have developed, or in some very fancy term we can call it a solar simulator. Why we use the solar simulator? Because under outdoor conditions it's very difficult to get a constant solar irradiance for longer period of time. So when we have to carry out experiments for more than 2 or more than 1 solar collectors, then it becomes very difficult to maintain that same ambient conditions or same environmental conditions. So that's why we use some artificial lights in order to generate the similar outdoor conditions, but inside a indoor setup. So this is the light source. From this light source, lights are falling onto the collector surface. This is the collector, and this is how the fluids are flowing. And we also use the IV analyzer even in the indoor setup to get the different electrical parameters of the PV modules. And to get the thermal efficiency measurement, we calculated the fluid outlet temperature, inlet temperature. We also use fluid tank with heater so that different inlet temperature conditions can be generated. Flow meter has been used in order to measure the flow rate. And we also use a fluid reconditioning system, because when the fluid comes out of the collector, it's at a very high temperature, like around 40-45. But to make to condition this fluid to the fluid inlet temperature range, we need to cool it down. Therefore, we have used a heat exchanger here at the outlet point. And this is the equation how we calculated this collector efficiency. This is basically the thermal efficiency. And this photograph tells us how exactly this setup looks like. And these are 3 important parameters which we need to investigate while designing an indoor test facility. First is the spectral match. That means by using the lights or artificial lights, how much closeness we are achieving to actual solar spectrum. And second is non-uniformity. That means suppose we are placing the collector and from the light source, is the light falling on every point of the modules at a constant rate, or it's varying? So for doing that, we put some grid points onto the collector plane, and we measured temperature, radiation at various points, and then finally using this equation we calculate non-uniformity, and that has been found to be around 4.16 when the collector plane was at a distance of 50 centimeter, and around 5.71 when the collector plane was at a distance of 40 centimeter. That means when we take away the collector plane, or when we increase the gap between the light field and the collector plane, then uniformity decreases, or non-uniformity increases, in the other words. But if we increase the gap between light field and the collector plane, the level of irradiance also decreases. So we have to take care, we have to get an optimum level where we get both a good radiation level as well as a acceptable range of non-uniformity. Then final parameter is temporal constancy or instability. So temporal means with respect to time. So we considered few points, and at that points we calculated the radiation for a longer range of time, and we found out how the lights are fluctuating, and we found that that's within very acceptable range. And this indoor test setup which we developed, that corresponds to class C of solar simulator. There are three classes of solar simulator: A, B, and C. A is the best one, which is the commercial one, B and C. But this is because this was done at a very minimal cost and without using xenon lights. For solar simulator, basically we have to use xenon lights, but due to a capital or cost monetary constraint, we tried to develop this setup using halogen and basic LED lights. So this comes under class C of solar simulator. Then formulation, these are different efficiency parameters we measured. I'll not go deep into these parameters: electrical efficiency, thermal efficiency, then energy and exergy efficiency. And we carried out a numerical investigation. Now I'll talk about why we have developed this model, or thermal modeling we have carried out. Because in PVD modules, people have used absorber sheet along with the tubes. Now what we thought, because as we know, if this is the thermal model or thermal energy interaction diagram for PVD module. In PVD, as we have in earlier slides, we have discussed that there are almost 7 layers, and between 7 layers there are almost 6 interfaces. That means there are 2 different metals are joined at one interface. That means 7 different materials or 7 layers of different materials, and there are 6 interfaces exist, and at each interface there are some resistance to thermal energy flow. So we come up whether this absorber sheet is useful for a PVD, or we can directly glue the tubes into the PV rear surface. There are 2 situations, so we need to find out which is the better one. So we developed these PVD models. What happened in earlier models, most of the researchers, they have neglected the effect of this thermal contact resistance at the interface of the layers, of the different layers. But in this new model, we try to incorporate this a new term called thermal contact resistance, and we try to find out whether this metal absorber plate is useful or not. Then we calculated different parameters like conductances, thermal conductance, and apparent pressure, asperity ratio, roughness of the surfaces. And then we finally developed a range of a set of equations. This is the resistance network diagram. What are different resistances that are exist between different layers? And we come up with this set of equations. So we compared these equations with one of the well-developed model that was published in Energy Conservation and Energy Conversion and Management Journal, and another article which also talks about thermal model of a PVT, but there they have not considered the contact resistance. We considered that as our reference model, and we try to validate these two models using MATLAB and experimental data. And we found, while calculating the temperature of various layers as well as the output fluid of the PVT, there is a considerable increase in the root mean square error of our present model. That model we have developed considering the thermal contact resistances between different layers. And we found that if we consider the reference model, which gives us 5.98 Kelvin of root mean square value for PV cell temperature prediction, but our model gives us a root mean square value of 3.27 Kelvin for PV cell temperature prediction. That means we have improved almost 2 Kelvin improvement in the prediction has been reported. So similar improvement has been reported for water temperature prediction. We have considered these two parameters because these are two parameters which are required to arrive at the efficiencies, because PV cell temperature, from PV cell temperature we can come up with, we can derive the PV cell efficiency, and for water temperature, from water temperature we can derive the thermal efficiency. Then we from the different PVTs we have studies where we on our experiments has been carried out. We found that rectangular spiral, or the M3, I'll call it rectangular spiral PVT, was found to be the best one. But one problem but still the cooling uniformity of PVT was not appreciable. Though it improves the, when rectangular spiral absorber or tube assembly was used, we reported a sufficient increase in the efficiency, but still the cooling uniformity was not up to the mark. So we tried to incorporate phase change material. Again, we faced some problems. What happens when phase change materials are used? When the phase change material undergoes phase transition, that means we use some solids behind the PVT, but when the temperature of the PVT goes up, this PCM melt. Due to melting of PCM, it's very hard to contain that behind the PV modules. So it adds up some additional cost. So we tried to come up with a solution where PCM can be used, but that PCM doesn't leak when it undergoes phase transition. That means it changes the phase, but it doesn't leak. So we tried to come up with a form stable PCM biochar composite. So this is how we developed the PCM biochar composite. We optimized the biochar parameters. We tried to come up with a noble biochar, which was derived from water hyacinth. And this biochar was derived at around 550 degrees centigrade of temperature, like the pyrolysis temperature of 550 degrees centigrade, where we received the best quality biochar. And then we mixed this biochar along with PCM. And then we kept it inside a oven at around 45 degrees centigrade for 16 hours, because this 45 degrees centigrade was used because this PCM has a melting point of around 35. If we have to use some PCM of around 100 degrees centigrade, then obviously the oven has to be kept at a temperature which is above 100 degrees centigrade. Then we come up with a composite, which is a mixture of biochar as well as PCM, and we analyze its leakage. This is how we come up with the biocomposite material. Water hyacinth has been collected from the nearby ponds. Then these are dried and grinded, then pyrolyzed. Then biochar and PCM, paraffin wax, PCM, this is PCM only, PCM are mixed and put inside oven. Then natural cooling has been done. Then we finally carried out the leakage test. And leakage test has been done for various proportions, like for 40% of the PCM and 60% of the biochar, 50% of PCM, 50% of biochar, 60% of PCM, 40% of biochar, like that. And we found that when 60% of PCM and 40% of biochar has been used, that gives us the best result in terms of leakage. That means there are minimal leakage has been reported. And then we carried out some basic characterization of this composite. The left hand side picture, that is the figure A, that shows the same image of the biochar, water hyacinth biochar. We can see there are various pores present inside, and the pore size of this biochar was around 11.92. That means it comes under mesoporous structure, and the mesoporous structure is best for absorption because it is not very high nor neither very less. So this is the same image of the biocomposite. That means when we added PCM into the biochar, these pores are filled with biochars. Now then we carried out thermal conductivity, and we reported from experimental studies, we found that when we use biochar as additives or supporting matrix for the PCM, the thermal conductivity has been improved by 48%. But this was not very large improvement in the thermal conductivity. Therefore, we added some metal powders. We use aluminum metal powder, and we found that when we added aluminum metal powder into the PCM biocomposite mixture, we achieved around 87%, 82% improvement in the thermal conductivity. And these are some of the well-established experimental works, or these are some of the products which are related to PCM biocomposite, and this is our product. And we found that our results are comparable to these international standards. Then we also carried out some chemical characterizations like XRD and FTIR, so in order to find out whether when we mix PCM and biochar, is there any chemical reaction or not. And we found that there is no chemical interaction between PCM and biochar. Then we carried out thermal analysis, like we tried to find out what is the thermal stability when we add biochar into the PCM, and we found that PCM degrades at around 128 degrees centigrade, whereas the PCM biocomposites start degrading at around 250 degrees centigrade. That means there is significant improvement in the thermal stability. We also calculated the melting temperature as well as the heat of fusion. Heat of fusion was found to be 78, as well as the melting temperature found to be 31.5 degrees. That means from 35, pure PCM has 35 degrees centigrade of melting temperature, which is reduced to around 31.5 degrees centigrade, and this is very optimum for application in the PVD collectors. I'll tell you why. Because after 30 degrees centigrade, the PV temperature goes down with each degree rise, and if we have a PCM that can be incorporated into the PV cooling, which have a melting point of 31 degrees centigrade, that means PV can be maintained within this range, below this range. So this is how we incorporate this biocomposite PCM plus biochar into the PVT. We put this composite into the rectangular spiral PVT collector, and we covered the entire back surface. This improves both the contact surface area as well. We have to be very cautious while putting this biocomposite, because this biocomposite is found to have a very high affinity towards absorption of moisture. So while doing that, we try to cover it up with some plastic sheets before putting a final enclosure. Then we try to find out how this PVT with novel form stable PCM biocomposite behaves under real-time conditions. This thermal imaging is showing like how effective this setup or this system PVT with PCM biocomposites. Before, like this complete rate collector or the left-hand side collector is without any modification. This is normal PV, and the right-hand side was the PVT collector with PCM biocomposite. So this red shows higher temperature, this blue or purple shows lower temperature. So from the figure B and C, we can see B shows the PV average temperature, which is around 43 degrees centigrade. Under the same condition, the PVT gives us an average temperature of around 30.6 degrees centigrade. That means there is a reduction of almost 12.5 degrees centigrade has been reported. And due to this decrease, 12 degrees in temperature of the PVT, we can find that as compared to PV, the PVT gives us around 18 watt more power output under the same ambient conditions, as well as when we use this PCM biocomposite, the degradation of the thermal efficiency under when the temperature of the outlet fluid decreases is not very drastic. This black black marks that shows the thermal efficiency of the rectangular spiral PVT without incorporating the PCM biocomposite. When the temperature goes down, we can see there is a sudden decrease in the thermal efficiency. But when we use PVT PCM biocomposite along with the rectangular spiral PVT, this red marks shows, and we can see there is not much drastic change. That means in this region, the temperature that was stored by the PCM start releasing, and the water start collecting the energy that is stored in the PCM biocomposite. So these was my, like, some in a nutshell. I tried to present my PhD work, and now I would like to welcome some of the questions that may be related to research, or that may be related to your careers or your further opportunities. Or you may ask me, like, mostly related to research career. You can ask me about how to different prospects in the field of energy. I'm happy to reply your questions, your queries. Thank you, sir. Thank you, everyone.